And so we begin chapter 9. It's titled Buffers. We're going to learn about the Henderson-Hasselbalch equation, buffer capacity, and plenty of other things in this chapter that are very important. All right, let's get started. So what are buffers? Buffers consists of a mixture of a weak acid and its conjugate base. A buffered solution will resist changes in pH when small amounts of acids and bases are added or when it's diluted. Biochemists are especially interested in buffers because many of the biological systems depend on pH. Buffers work because the added acid and or base is being consumed by that buffer, which of course resists changes to pH. As more acid or base are added, then that resist to change lowers. As you notice here, this is the Henderson-Hasselbalch equation, which is the main equation, the central equation for buffers. So whenever we talk about buffers, we're going to see this equation pop up. And if you notice, all the HH equation is, it's a rearranged form of the Ka equilibrium expression. There's your Ka. It's obviously products over reactants. And what they've done is they've taken the log of both sides, and you can see what happens to the right side. And we want to keep the A minus and the HA together, basically the conjugate base and the conjugate acid together. So that's why they split up that fraction in that particular manner. If you don't know your logs, or you don't know the rules for the logs, there's a useful little side note on page 190 of your book that kind of helps you remember how to work with logs in certain situations. So they've split it up, and now you see that they've put things on separate sides, and they have the negative log of pH, which is the pH, that's the definition of pH. What's the negative log of Ka? That's the definition of pKa, plus the log of A minus over HA. So really, it's just a rearranged form of the Ka equilibrium expression. So the HH equation will tell us the pH of a solution, provided that we know the concentrations of acid and the concentrations of base and the pKa of that acid. So here's the HH equation for an acid. Obviously, here's your acid dissociation reaction. HA is broken up or dissociated into H plus and A minus. And there is the Henderson-Hasselbalch equation for an acid. And it's exactly what we just sort of derived in the previous slide. Now this is the analogous equation for a weak base, where the pKa is the acid dissociation constant for that weak acid, which is the BH plus. The important things to note here is that the base always goes in the numerator of the HH equation. If you notice, the A minus is on top and also the B is on top, which is the base, the weak base of those equations. And the acid always goes in the denominator. And remembering that for the base HH equation, this pKa right here is the acid dissociation for the weak acid, which is the BH plus. Now I realize that you're not familiar with this particular version of the weak base equation. Usually what we have seen before is base, or the weak base plus water, is in equilibrium with its weak conjugate acid, BH plus, and OH minus. But this is the same equation, just written from the starting point of the weak acid. When the concentrations of your base to acid, your weak base to your weak acid, when those concentrations are equal in that HH equation, that log term is 0. Because remember, log of 1 is equal to 0. So when that happens, when the concentrations of the weak acid and the weak base are equal, that means that the pH is going to equal the pKa. So keep that in mind when you look at problems. Now, another thing to remember is when the ratio of your weak base to your weak acid changes by a factor of 10, then that pH changes by a unit of 1. And we should know that already, but I just wanted to remind you of that. And another thing to note is that as the concentration of A minus increases, then the pH must go up. And as the concentration of the weak acid increases, then the pH must go down. Go through that carefully and make sure you understand that. So let's do a quick problem that deals with the HH equation, or buffers. Sodium hypochlorite, and I've given you the molecular formula, which is the active ingredient in bleach, was dissolved in a solution buffered to pH 6.20. Find the ratio of the weak base to the weak acid in this solution. So OCl minus is the conjugate base of hypochlorous acid, which is that HOCl. The key word in this problem is buffered, so you know more than likely we're going to have to use the HH equation. So go ahead and write that down. pH is equal to pKa plus the log of products over reactants. Now the product is going to be your weak base, the OCl, because remember, this is sodium hypochlorite. It's dissolved in a solution, so when it's dissolved, that Na is going to trade places basically with your water, right, the H. So you're going to start off as your HOCl, and that's going to be in equilibrium with your weak base, OCl minus, plus your H plus, which will dissociate. So we need to find out what the pKa of this HOCl, by the way, and I said it already, that's hypochlorous acid. So go to the back of your book, and if you do that, you will find that the pKa is 7.53. Now, we know the pH because they told us. So if we wanted to find the ratio of that solution, then all we would write is plug in 6.20 for the pH, plug in 7.53 for the pKa, and then do the log of OCl minus over hypochlorous acid. We bring the 753 over to the other side, and you'll see you'll get negative 1.33 is equal to the log of OCl minus over HOCl. Now you have a log. So to solve for this, you got to raise 10 to the power shown on each side. So if you raise 10 to the power of negative 1.33, you will get 0.047. If you raise the right-hand side, which is just the log of this ratio with letters, all you're going to get is just those ratio with letters without the log. So our answer would be that the ratio of OCl, of the conjugate base, to the conjugate acid of this solution is equal to 0.047. So again, finding the ratio of the weak base to the weak acid requires only the information from your pH and your pKa. You don't care what else is in the solution, how much NaOCl was added, or what the volume of the solution is. It doesn't matter. All you need to know is pH and pKa. All right, let's move on. This example shows a buffer in action. There's a widely used buffer. It's really common. It's called tris, and it's short for this awfully long name that you see there, tris hydroxymethyl amino methane. I would never remember that if they didn't tell me. But anyway, tris. Now, you can see that the BH plus is the conjugate acid of tris because they've added that one proton to that amine on the top. An example of a salt containing this BH plus would be something like tris hydrochloride, which would be in the form of BH plus Cl. Now, when BH plus Cl is dissolved, it completely dissociates in water. Now, the question reads, find the pH of a 1 liter aqueous solution containing 12.43 grams of tris, they give you the formula mass, plus 4.67 grams of tris hydrochloride with its formula mass. Keywords here are tris. You know, if you see that, you should be able to realize, okay, this is probably dealing with a buffer, so let me go ahead and write the HH equation. So pH is equal to the pKa of, and since I know that tris is a weak base, I'm going to go ahead and do the weak base HH equation. So pKa plus products, which is the base, the weak base, over the weak acid conjugate, BH plus. After I do that, it basically is very simple. All I got to do is figure out what the molarity of each of these compounds are. And they've given me the mass, and they've given me the formula mass. So all I got to do is convert to moles, and they tell me it's over 1 liter, so there goes your molarity. So 12.43 divided by 121.14 grams is equal to 0.1026 moles of tris, which there also means 0.1026 molar of tris. You do the same thing for tris hydrochloride, the BH plus Cl, and you'll get with its formula mass, and you'll get 0.0296. Now, you plug those two numbers into your pH, in your HH equation, and you should get pH is equal to 8.07. How did I know it was 8.07? It told me in the problem right there. The pKa of my weak acid conjugate is 8.07. So pH is equal to 8.07 plus the log of 0.1026 divided by 0.0296. I divide those two numbers, I take the log of those two numbers, and you should get 0.5398, so on, so on, so on, and so forth. You add that number to your 8.07, and you'll end up getting 8.61. So the pH of a solution with that many grams of weak acid and weak base conjugates of tris happens to be 8.61. All right, guys, that does it for this part of buffer videos. I'm going to do one more video that deals with buffers, and then we're going to move on after that. See you later. Bye-bye.